Well, this is the final lecture video for our class, and as perhaps appropriate, the sun is setting on our class, so we're going to talk about the sun, and I thought I would pick this image here. As you can sort of see from the light, it almost looks like I am sunburned, and I'm not sure that the red shirt is really helping all that much, but I will continue on with this. I wanted to point out one thing. A couple of people have mentioned, because I do gesture along the way, and some people have noticed this, this little bracelet thing that I have here. Oh, my hand disappeared. Imagine that. They're trying to beam me out. This is actually the solar system, and each of these beads represents a planet or a moon or the sun. And in particular, you can see this one here. I'll try and get it closer here. You can see it's Saturn with a ring around it. And we have Jupiter before it, and Mars, which is red before it. We have Uranus, which is a little bit greenish, and Neptune, which is bluish. So a friend of mine got that for me, and I've been wearing it sort of ever since. I almost forget that I have it on, but thank you to those who have commented, what's that thing on his arm? So I thought I would highlight that. You would think, though, that the sun would be much, much larger. If this is, in fact, the size of the planets, if this is the size of Saturn, and this is the size of Jupiter here, then in fact the sun would probably be somewhere between a softball and a beach ball in terms of size. So that really wouldn't fit on my wrist. But the sun is large, the sun is powerful, the sun is a star. It is the star of our solar system, no pun intended there, because it really is. So we're going to take a look at it. Many chapters, many books have just one chapter on the sun. And most astronomy courses like this have 1 week on the sun, and not literally on the sun, that's too hot. But for some reason, your textbook breaks it into 2. I'm blending it back into 1. So this is an all-in-one chapter lecture for chapters 15 and 16. So I hope you enjoy it and stick with me here. I am taking out a lot of physics and a lot of mathematical things because our class is supposed to be conceptual, not mathematical. So I think that's why it makes sense to combine the two together along the way. But I will try to share my screen here and see what we can do. And it looks like we are at the start of the slideshow. So here we are. 15 and 16, the sun. The sun is our star. It is 1,000 times larger than Jupiter. It is something that is the most powerful thing for about 4 light years in every direction. So if you think about how far away things are in our solar system, multiply that by about 50,000, and we're still sort of focused on this star as the primary energy source, the primary gravitational source. And certainly for us here on Earth, it is the primary reason why we go around the sun and have a year. We're attached to it by gravity, and we are enveloped in its energy. So that's why we have life on our planet as well. Take away the sun and there's not enough energy for life here. Certainly not in the complexity that we have it. So all hail the sun in different ways, but the sun is mysterious in many ways. And you would think that looking at the sun, don't look directly at the sun, but looking at the sun for thousands and thousands of years, we would have thousands of years of understanding of it, but that is really not true. It's only been barely 100 years that we've had any real insight into what's going on inside. For a long time, people thought it was a ball of fire, and it seems like a ball of fire. And every now and then I will, in the course of this lecture, talk about it in terms of burning. But when we talk about burning and fire, we're typically talking about a chemical process. And we can do that here on Earth. We can burn paper, we can burn wood, we can burn gasoline, we can burn any number of things. Those are chemical processes. And when we look at the chemical energy that we get from those processes, we can measure how much heat is coming off of a fire in a fireplace. We can measure how much heat is coming off of, or how much light, how much luminosity is coming off of something that we're doing here on Earth. We've discovered that based on the amount of energy coming off of the sun, if it were a chemical fire, it would only last about 10,000 years. Now, if you're a young Earth creationist and think, what's the problem? The Earth's been around for 6,000 years. The main problem is when you're burning something chemically, there's always something left over. There's always ash left over. There's always some leftover something. If we're more than halfway through the life cycle of the sun, based on how much stuff is there and how much light is coming off of it, there'd be a lot of ash, and there's none there. So we sort of have figured out it's not Apollo's chariot wheel on fire, and we've going through the sky, and we've sort of figured out that that's not really the case. But then in the 1800s, so see, for most of human history, we had no idea. We had no idea. Up until the 1800s, people began to understand that there were other ways of generating energy. And one of the ways was gravitational energy. Is it contracting? When things are contracting, they are giving off energy. So when we are thinking about that, two guys we can think of in particular are Kelvin and Helmholtz here. William Thomson actually became Lord Kelvin. He became sort of the grand old man of science during his age, sort of Victorian England. If you've ever seen movies or shows that deal with that time period, he would fit right in there. We even have a temperature scale that's named in his honor because he's the one who pretty much put it together. The Kelvin scale starts out at absolute zero. But one of the things that he and others at the time were figuring out is that gravitational contraction generates energy, and that might give us a longer lasting sun. So if we, again, take measurements of the light coming off of the sun and how much matter is there, we can figure out it would last about 25 million years. Well, that's a lot better than the 10,000 years. We don't have to worry about it burning out anytime soon with that. But it wasn't really figuring out how to mesh with other things that were being developed in science at the time. Geology was beginning to say that the world was much older than 25 million years. And in fact, 25 million years doesn't even get us back to Jurassic Park, which would be 65 million years ago. So we had to conclude that there's still something else missing. So the answer is no. So it wasn't until the early 1900s, as I said before, barely 100 years ago, that we figured out what nuclear energy is. The sun is actually a nuclear generator, and it generates energy according to our famous equation here, E equals mc squared. Now what this means, this equation, very simple to understand. E is energy, m is the amount of material, mass that's here. C is the speed of light. If you remember way back a couple of chapters, we were talking about the speed of light. That's 186,000 miles a second, or 300,000 kilometers per second, 300 million meters per second. This equation is actually denominated in meters. So when we talk about 300 million times 300 million, we're talking a big, big, big number here. That's what that square means. So you only have to have a tiny amount of matter to get a big, big E, a big, big energy sense there. So by the time we put that together with how much stuff is in here, the sun lasts about 10 billion years. Here's the other thing that gives us a clue that this would be right. Again, just like if you're burning something, you have leftover ash. If you are converting nuclear energy from matter into energy, you will have leftover stuff. You will take hydrogen and turn it into helium. And when we look at the sun, we see that's what's happening. The hydrogen is turning into helium as the energy is being produced. And we'll talk about that a little bit later in our chapter here. The people who are perhaps most to be credited with that, of course, Albert Einstein, looking here sort of very dapper in his earlier days. It would be later that his hair would go in the typical way we're sort of used to seeing. And Wolfgang Pauli. And Wolfgang Pauli was someone who figured out that there's a lot more than meets the eye about the sun, including neutrinos. And we'll talk about neutrinos. Those are other particles that come off of the sun as well. Our sun is 93 million miles away, so less than 100 million miles away. All other stars are billions and billions, if not trillions and trillions or quadrillions and decacillions and all other kinds of numbers that we go beyond the imagining away from us. So the sun is the only one in what we would call our local neighborhood, the only one in our solar system. So we're still trying to figure things out with the sun. It's actually not a very big star. It's a yellow dwarf star. I will put up a video that will show you how large a star can get. And in fact, as I'm thinking about that right now, I'm going to write it down. So I will remember video on solar system sizes and stellar sizes. So there we go. Okay, because I get to the end of all of this and I forget. It's like, what did I say I was going to do? That tells me there. What we have is a big ball of gas that is superheated. It is charged plasma. It's mostly hydrogen and helium, which is what most of the universe is. And what's happening inside is that it's turning hydrogen into helium by a fusion process. We'll talk about nuclear processes here in a couple minutes. As we're looking at the sun, gravity is pulling in and the energy it's generating is pushing out. And that's in more or less of a balance, so we call it a hydrostatic equilibrium. Now, hydro usually implies liquid here, but we're sort of using this with the plasma that gravity pulls in and energy pulls out. Now, the sun does pulse just a little bit. It's not just sort of perfectly rigid. As it expands out, it cools off a bit. As it cools off a bit, gravity takes over and pulls it back in. As the gravity pulls it back in, it heats up again and it expands out. So it does pulse just a tiny bit. There are other stars that pulse quite a bit. And if you take the 102 class, we talk about some of those stars. We have variable stars called Cepheid variables, and we have pulsars. In fact, the North Star is a variable star. If you look at the North Star, sometimes it looks dimmer and sometimes it looks brighter. That might not be your atmosphere or your eyes. It may be the star itself. So as we're looking at the sun, we have some different structural parts to it. The core is where the energy is being generated. It's probably about 15 million degrees in there. The core has the fusion processes happening. As the energy is escaping, it's radiating out, so we call it the radiative zone. Sometimes it takes a particular piece of matter, just 50,000, 100,000, your slide here is saying 100,000 years to get from the core through the radiative zone. That's a long, long time, and I'll come back to that here shortly. The convective zone is where the energy sort of begins to regularize and dissipate a little bit, and so it glows around the photosphere. Photo meaning this is the part that we see if we look at the sun. If you're sort of looking at the sun over here, don't look directly at the sun out the window. But this is the surface. Then we have an atmosphere, which includes chromosphere and corona. And of course, these are much more gassy and wispy areas along the way. The convective zone, the convection zone, consists of boiling bubbles, sort of like we have when we boil water. Here, the hot stuff rises, releases the energy, the cooler stuff sinks back down, and we can actually see that on the surface. This is a picture of the surface of the sun, sort of looks like melted caramel. And we can see the darker stuff is where the energy is sinking, or the gas is sinking back down after the energy has been released. These brighter areas are where the energy is being released. So these bubbles will grow and they will release their energy and then they will fall back down. And that can take place in a matter of a couple of hours. So this is a pulsing and bubbling kind of surface. And we call this granulation. Each one of these is called a granule. And there can be maybe as much as 1,000 degrees temperature difference between these bright areas and these darker areas here. The hot gases are rising, they release the energy, then the cool gases sink back down and pick up more energy from the radiative zone. But as we see energy being produced in the center of the sun at 15 million degrees, by the time it gets out to the surface that we're seeing, the tops of those granules, it drops all the way down to under 6,000. I mean, it's a big drop. If you started out with $15 million and went down to 14 million, then 13 million, then 12 million, then 10 million, then 9 million, then 5 million, then 1 million, then 100,000, then only 6,000, you've lost everything. You've lost almost everything. Almost all the energy is lost on its way out because the sun is so dense. All the particles are hitting each other along the way and releasing energy inside. So by the time it gets to the surface, it's really low. But as soon as it breaks free of that, it heats up again. It shoots up to as high as 1 million. So the corona, the gassy area just outside of the sun, is a lot hotter than the surface. Now, as I mentioned, inside we have a nuclear process. There are two different types of nuclear processes that we typically talk about. We have fusion and fission. And fusion process is when things bind together, we fuse them together. Fission is when we split things apart. And fusion happens with smaller things. We're making larger things. Fission starts out with larger things, usually uranium, and splits it into smaller things along the way. Now, when this happens, we get energy produced according to, again, our famous equation here, E equals mc squared. And what is happening is when uranium, for example, in a fission process splits, notice it says uranium-235 here. That means there are 235 particles in this atom, in the nucleus of this atom here. Not all of them are protons. In fact, most of them are neutrons. So we have our protons and neutrons that are going to be split apart. Some of them will end up being just free neutrons. Some of them will be smaller elements. But some of that matter there will end up converting into X-rays and other energy. And that happens according to this equation here, which is why you can start out with really 10 or 15 pounds of uranium and really do a lot of damage to a location when it explodes. Those kinds of fission processes are called uncontrolled fission processes. We do this same thing inside of nuclear power plants, and those are called controlled fission processes, hopefully, as long as the plant doesn't break down. Fusion we can only do as uncontrolled. Those are hydrogen bombs and fusion bombs. We haven't figured out how to make a fusion process not burn the place down, not melt the place down. But it is actually the most efficient way of these to make energy. You start out with two hydrogen atoms and you thrust them together under very high temperatures. Remember the sun here, 15 million degrees, under very high pressure too, and it pushes them together and it makes part of a helium atom's nucleus. So see, we have two portions here, which are H2, because we've still got just one proton. One of these is turned into a neutron. When that happens, it generates a little bit of energy. Then that duo here, we would call this deuterium, it's still a version of hydrogen, gloms together with another proton, another hydrogen that's just out there in the soup, and it turns into, now notice this is He, this is helium, this is 3 pieces. It's 2 protons, however, and 1 neutron. Because it's got 2 protons, it's now helium rather than hydrogen. Then we've got these triads here that are floating around that get slammed together, again, same pressure, same temperature, and fuse into a stable helium atom, which is 2 protons and 2 neutrons, releasing some hydrogen protons back into the mix to start the whole process over again. This whole thing is called the proton-proton chain. You start out with 4, and you end up with 4. You have some helper protons, I'll call them, along the way that get then recycled back into the mix. But at each step here, notice we have energy being created. And that energy amounts to E equals mc squared. Only about 0.7% of the matter is lost. 99.3% or maybe a little bit more of the matter is still there in the helium atom. Now we've been trying to set up our own kinds of fusion reactors. This actually looks like a big Lego set to me. But one of the things we try to do is we try to use different ways of working with the atoms to fuse them together and generate energy. We have yet to figure out how to do this on an economical and long-term basis. But I would suspect in the lifetime of most, if not all of the people in our class, we'll figure this out because technology goes rather quickly. Now, as I mentioned, the sun is a gas. The gas is in particle form. You can increase the pressure of gases by adding temperature or by adding more particles. So inside of the sun, as we have all of these particles that are floating around and slamming into each other and making heavier and heavier elements in hydrogen into helium. Helium is a heavier element than hydrogen. In later, bigger stars, that helium will turn into larger and larger and larger things. Our sun won't quite get there. But inside of this soup, we have the energy being produced, and we call those particles of energy photons. Photons are being generated, and they're bumping into all of the particles. They are trying to get out. They're trying to escape. But as they are doing this, each time they bump into something, they have less and less and less energy. Hence, the temperature goes way, way, way down. Now, the sun to our planet is 93 million miles. And it takes a photon from the sun to our planet about 8 minutes to get here at the speed of light. Remember, 186,000 miles per second, 300,000 kilometers per second. It takes about 8 minutes for the light to get from here to there. So what's happening inside the sun, however, as I mentioned before, the photon starts in the center and has to reach the surface. That's nowhere close to 93 million miles. We're not even talking a million miles here. And yet that can take anywhere from 50,000 to 100,000. Here in this slide, it says up to 1,000,000 years for the energy to get to this point here from the center to this. Then if this was the size of the sun, the Earth would be a football field or more away. It would only take 8 minutes then to get the rest of that way. One of the exceptions to that is the neutrino. Neutrinos are ghostly particles that just zip right through the sun because they don't interact with stuff. There are neutrinos going through your body right now and not interacting with anything. Well, how do we know all this? How do we know that we have this interior structure of the sun? We haven't landed on it, obviously. We can't drill down and find out. But we can tell what's happening from the energy that comes off, and we can tell by watching the surface what's happening underneath. Because again, mathematics, and I took all the math out of this lecture, so to a certain extent you need to trust me, or take more astronomy and do the math yourself and you'll figure out how it works. We can work with hydrogen, we can work with light, we can work with temperature, we can work with things under dense conditions here on Earth, and we can figure out how these things work here on Earth in smaller forms and then apply those to what we're seeing coming off the sun, and our theories tend to fit. Our temperature goes way down. Our density goes down. The closer you are to the center, the more densely packed things are. The closer you are to the surface, the less it is. The percentage of hydrogen that's in there, the percentage of light that we're getting off. So all of these things work. And when we're looking at the surface of the sun, again, we see our granulation and our bubbling, and we have our oscillations. One of the things that we see is that some of these surface areas are sort of pulsing out, some are pulsing in. So we end up with this oscillation effect. Our sun is pulsing a little bit. And in addition to this, we get sunspots. Sunspots it can be analyzed particularly through magnetic understanding, because these are magnetic activities happening here. We have strong magnetic fields that are going around it. So we have something called helioseismology. If you think about the word helium, that means sun. The Greek word for sun is helios. So helium was first discovered on the sun before it was discovered here on Earth. That may be a quiz question that's worth remembering. The reason why helium is called helium is we thought it was sun stuff. We never discovered it here on Earth before we discovered it on the sun. But seismology. You may have heard of that too. I probably mentioned that word when we were talking about the Earth. This is what we do deal with when we're talking about earthquakes. So we have quakes on the sun. We have sun quakes. And a lot of those have magnetic effects. Now, some of the different ways we can see what's happening with the sun is we can take measurements, we can look at the light. Again, don't look directly at the sun. We can point telescopes. Again, never, never, never do this unless you have the right filters. And make sure to put the filter on first. I had a friend ruin his telescope by pointing the telescope at the sun and then trying to put on the filter. And in that time period, the sun's heat magnified inside the contraption that he had of a telescope, because it was one of those that had different mirrors inside, and it just melted the whole thing. It was a nightmare. So yeah, it's sort of like a $5,000 glitch there. So don't point your binoculars at the sun. Don't point your telescope at the sun. Don't point things at the sun unless you're very, very, very sure of what you're doing. But the sun can get to you even if you're not doing anything. Notice this tank here. Notice there's a guy standing on the railing here. This is deep, deep, deep underground. It is meant to block any type of radiation that might come through the atmosphere or through even rock and other debris. So the only thing that's going to get through here are those phantom particles I mentioned before, the neutrinos. We have this full of a very volatile material. Probably this one is phosphorus. And what we have here is we're measuring anything that's getting through to hit it. This is another one deep underground. This one is another one in Sudbury in England. And Sudbury, notice again the size here, deep underground, I think in a salt cave, if I'm remembering correctly. And it also keeps anything but neutrinos from getting through. We have to do that because largely any other particles getting through are going to throw off the experiment. As I sit here right now, I have 50,000 neutrinos going through my nose and 50,000 neutrinos going through my eyeballs every single second, if not more. And it doesn't matter if I'm on the other side of the planet at night. You know, you have the sun here and you have the earth here, and over here on this side it's nighttime. So how are the particles getting to us? Well, they're just going right through the earth and they're going out the other side. So there's a lot of stuff being generated by the sun. Most of it, fortunately, is harmless to us or is blocked from being harmful to us by our atmosphere. Our sun does generate energy and does also generate particle flares. We have flares, which are explosions. We have even things called coronal mass ejections, where it throws off a huge amount of material along the way. Sometimes we can see these kinds of loops that are coming. Here's the Earth for comparison. Now, you don't have to worry that one of these is going to sort of fly up and whip our planet out of its orbit, because again, if this was the size of the sun, the Earth would be a couple of football fields away down in that direction. If this were going to influence any planet at all, it would have hit Mercury a long time before us because it's closer. It would have hit Venus before us because it's closer. So we don't really have to worry about that. Most of the material being ejected up here is going to be pulled back down by the gravity of the sun. Now, one of the persons who helped figure out using these kinds of things like solar flares, coronal mass ejections, and other kinds of data that we were getting from the sun to understand the insides of the sun was Cecilia Payne. And she later got married, so it was Cecilia Payne-Gaposchkin. Notice one thing here I want you to notice. She got her doctoral dissertation in 1925. She did not get her appointment as a professor until 1956. That's 31 years later. That's a long, 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 long time to wait. There's still some discrimination gender-wise and race-wise and otherwise in science as well as academia, as well as a lot of different places. Fortunately, it's less, but this, I mean, think about this. Whenever I remember the story of Cecilia Payne-Gaposchkin, I remember a woman that I had as a teacher of mine. And if this were a face-to-face class, I would be sharing this story. So I'm going to share it with you now. Her name is Mrs. Griffith. And if you ever remember, back in the 1950s, there was the sort of telephone operator who would sit at a desk, and she would have her headphones on, and it was almost always a she. And she would have these wires, and she would have to put these wires together, and she would be connecting phone calls this way. You would call into the operator, she would take your call and plug it into something else that would then send it on its way. We now have machines that do all that. We don't have to have people actually sitting in places doing that. But for decades of the way the telephone system operated, you had to have operators to connect calls, especially for long distance. We'll keep that image in mind. Mrs. Griffith was a math teacher of mine, and she had 2 master's degrees. She had 1 master's degree in what we call applied math, which is basically engineering types of math, telling how to use the math to figure out how heavy the dump truck can be on the axles that are being built on the truck, or how high the arch can go under the strength of the materials that are being used to build it, or other kinds of things like that. So she had a master's degree in that. She also had a master's degree in pure math, which is where you're talking about the theory of math and how numbers work with each other, irrespective of whether or not it applies outside of just the realm of numbers. Well, she took, and think about this sometime, how many of you have taken 15 credit hours in a semester? Now, those of you who have, how many of you have taken 18 hours in a semester? Those of you who have, if there are any still left standing when I ask that, how many of you have taken 21 credit hours in a semester? I've done that once, never again. Well, Mrs. Griffith, my teacher, took 21 graduate level hours all in math. She took 7 math classes all at the same time at the graduate level. And her dean said, I'll let you do this as long as you're not working part-time. And she crossed her fingers and said, I'm not working part-time. She was working full-time. You know where? Remember what I told you about the telephone company? She was the woman sitting there with the headphones plugging things in. She sat there 10 hours a day. You had to work 10 hours a day back then. And she had her math books on her lap, and she was doing math while she was connecting all of the stuff. She should have had a doctorate. And when she went to get a doctorate, her dean was very blunt with her and said, they won't give you a doctorate. They won't give a woman a doctorate in math. Don't let anyone ever tell you that you can't do it. Don't let anyone ever tell you that. So think about Cecilia Payne-Gaposchkin. Think about my teacher, Mrs. Griffith. Think about what you want to do and make sure you don't let people tell you no. If you know you can do it, you do it. But one of the reasons we know about all this stuff inside the sun is because people refuse to take no for an answer. So we know all of these things because we know the math. We know the pure math and we know the applied math, and we can put those together based on the readings that we're getting from all of those different things. So we still study the sun. We have lots of mysteries that we are still exploring, one of which is sunspots. Now, sunspots can be huge. Notice again, here's about the size of the Earth compared to just the sunspots on the sun. Sunspots come and go in a regular cycle. They are much cooler. They're 3,800 degrees compared to the rest of this out here, 5,800 degrees. So they're 1,000 to 2,000 degrees cooler. That's why they look dark. Now, if I were to take a sunspot clump and hold it up and show it to you, it would be the brightest thing you've ever seen in your life, and my hand would instantly disintegrate. But because it's up against stuff that's so much brighter and hotter, it looks dark from our perspective in pictures like this. Here's our granules, all of our granulation, our hotter bits that are poking through the surface, our darker pieces that are sinking back down, and here is a sunspot in the midst of this. Notice we have these little striations that are here. Now, when we look at it in black and white, we can see that even more pronounced. We can still see our granules around here. This dark area here, that's still going to be 4,000 degrees, 5,000 degrees. This area out here is going to be 6,000 degrees. So that's still going to be brighter than bright. but because it's up against this other stuff, it looks dark, and we call that dark area the umbra. You might remember that word from eclipses. The darkest area is called the umbra. The less dark area where you're in a partial eclipse is called the penumbra. So this would be this area around here, the penumbra. But notice again, it's sort of these linear striations. How many of you have ever gone to like a Stuckey's or a truck stop or something and got a picture of the guy with the iron shavings that you put the beard on and the hair on and all of that? You can do that because it's magnetic. Well, that's what this is here. This is magnetic. This is magnetized. And you know it has to be a powerful magnet because helium and hydrogen typically are not magnetic. They're not metal. They're not metallic. So how can you make them magnetized? Well, you can do it with the superpower of the sun. They're often in pairs. Sometimes they're more pronounced pairs that look like they're pairs. Sometimes they're a little bit sketchier. Sometimes they sort of are falling apart in different ways. I love the fact that this one here has this little band across the middle because that's probably a big loop of material that's coming off of one here. We can see them scouting through the sphere of the sun. This is another way in which we know the sun is a sphere because we see them move around and we see them sort of like this edge on, and then we see them like this, and then we see them like this as they're going around. That happens in 3 dimensions. That doesn't happen on a flat sphere. So again, we can see the sun rotating, we can see the sunspots moving, we can see them coming from one side and bending into the other side along the way. One of the ways in which we know they're magnetic is we have something called the Zeeman effect. If you have those spectral lines, remember you take your prism and you run the light through it and you get the lines that say I'm hydrogen, I'm helium, we talked about this before. Well, sometimes you get this 3-pronged effect here. And that's because the magnetic forces are pulling some of the light in this direction, some of the light in that direction. We're getting a 3-pronged effect as it's going towards the north, the south, and in the middle. Now, sunspots come and go over time, as you can sort of see here. Usually it's about an 11-year cycle. Sometimes we have a minimum cycle here. Sometimes we have a maximum cycle here. So these are things that we have noticed from the early 1600s. And again, thank you, Galileo. Now, Galileo looked at the sun. Don't look directly at the sun. His telescope did not have the warning label that not to look directly at the sun. So we're fortunate that he didn't do too much solar activity before he realized this was being damaging, also before he did some other observations that were critical along the way. Some people may have seen sunspots before Galileo. And again, like we were talking about with our exoplanets, we had discovered a few before we discovered the one in 1995 that we said, aha, 51 Pegasi, that is our exoplanet. And then we're like, oh, well, we'd seen these before. We don't count those because as discovery because we didn't know what they were. There may have been Chinese astronomers who saw sunspots, but they probably, if they saw sunspots, thought they were clouds going in front of the sun, because that makes sense. Nobody knew about sunspots back then. There may have been some other astronomers as well. But we give Galileo largely the credit for this because he's the first one to identify that they were in fact on the surface of the sun. But here's the thing, he was living in the early 1600s. Shortly after that time, we entered something called the Maunder minimum. Notice we had no sunspots for more than 50 years. And people were wondering, well, was this the unusual time or is this the unusual time? Because once they started up again in the early 1700s, they've gone ever since. We've had a low period here and a medium period here. But we've had sunspots consistently every 11 years since the Maunder minimum. We don't know whether this is the natural cycle and this is unusual. If, say, you spread this out to be 10,000 years or 100,000 years or 1,000,000 years, would more of it look like this or would more of it look like this? The answer is we don't know because we only have 400 years of data. The weird thing is when you look at the Maunder minimum here, that influence the climate of the Earth, some people think. So again, the jury's still out on that. But we had what was called the Little Ice Age during this period here. And there were all sorts of weird kinds of things that really persisted up until the middle of the 1700s. So we wonder if the solar sunspot cycle has something to do with climate change, because our climate has changed back and forth. Again, don't let anyone ever tell you that the climate change is untrue. The climate has been changing from the beginning of the Earth. The sun is sometimes pulsing, as I mentioned before. It is, in fact, getting a little bit brighter. We have our Maunder minimum and our sunspot cycles. We have ice ages. We have warming spells. All of these things are true. The main concern today is, are we as human beings making it better or worse? One of the interesting things I invite you to look at different websites about is take a look at China, take a look at Los Angeles, take a look at New York City, take a look at pollution over the last 2 months, when there have been major lockdowns and factories have been closed and lots of people haven't been driving. Notice the difference in the pollution, especially in the air, because that makes a difference as to how we see the sun, how the sunlight interacts with our atmosphere, and how our climate is adjusting. So we do make a big difference on the Earth, but we're not the only difference that's being made. As we look at the sunspots, we see them sort of grow and shrink, and they sort of grow and shrink in this butterfly kind of thing because they grow out. And this is the equator. This would be the North Pole and the South Pole. So they start on the equator and they sort of grow out and then come back in and grow out and come back in and grow out and come back in. Again, they often form in pairs. As we're looking at the sun in different ways, we can sort of see things like here in our X-rays at the bottom here. Lots of active stuff happening. Coronal loops, we have some openings, some gaps. When we're just sort of looking at it in regular light, we have here sunspots and our sort of yellowish coloration. When we look at it through what we call the H-alpha line, which is looking at it through hydrogen in a particular way, we can see this white stuff here in addition to some sunspots. That would be material that's something other than hydrogen. A lot of it is calcium. So our temperatures on the surface, again, somewhere around 6,000 degrees. Out just above it, it still stays that area, but as the energy is escaping, superheats some of the gas that's around, the temperature goes way up because it's no longer compact and it's no longer condensed. But this is one of the areas we're still studying and trying to figure out. Notice here, this is the sun's surface down here in the lower right. We have a lot of storminess. We have a huge area of storms and stuff that is just sort of being generated in all sorts of weird and wild ways on the surface of the sun. A lot of these images come from a cooperative program through NASA and JAXA, which is the Japanese space agency along the way. When we see the sun in a solar eclipse, we get to see various bits of the corona, but we don't get to have solar eclipses very often. And if you have a telescope that's in one place, you get solar eclipses even less. So we have what's called a coronagraph. We can block out the sun and see what's happening in its atmosphere above. We can also look at it in different ways. What we're seeing here, this is largely an X-ray kind of image. We see lots of solar storms. We can see some solar explosions, and we see what's called a coronal hole, which is an area of sort of calm and lacking in gases. And we can see that stuff moves. We've got these really wild kinds of hurricanes, and these are each larger than the Earth around this area. It reminds me sort of the shape of Italy, the boot that's here. So as this is happening, particles are moving every which way in the storm, and some of them get flung out, and some of them make it as far as the edge of the solar system, but quite a number of them hit us here on Earth as well. And when they hit us, they interact with our magnetic field and give us our northern lights. So especially when we have a huge burp from the sun called a coronal mass ejection, that's what a CME is. And I'll show you a couple of pictures of those here in just a moment. But they form the northern lights and the southern lights. And here, this little GIF, it's not in your regular packet in the classroom. I just found this a few days ago. But notice as the particles leave the sun, they will hit the magnetic field of the Earth. The magnetic field of the Earth looks like it's bent out of shape a little bit here. That's because the sun's power, the solar wind, is pushing it out in that direction. But as the particles rebound into our sort of magnetic vortices at the north and the south, we end up with our northern lights. And one of the reasons I go to Iceland as often as I do, anyone who knows me knows that I go there, it's because you get this. You get this quite a bit. Notice the purple stuff that's in there in addition to the greenish color. You get quite a lot of different stuff there. That purple stuff is slightly different in terms of the energy and interaction that's happening. And the technical word for that is Steve, which is weird, I know. But look up Steve, look up Northern Lights Steve on Google sometime, and you won't be disappointed. It's rather interesting. But you can sometimes see the Northern Lights even here in Indiana, but you typically have to be north of Indianapolis, because even here down in Bloomington and Bedford and Martinsville, Spencer, Nashville, Columbus, the city lights from Indianapolis are actually in the atmosphere all the way down here. And the Northern Lights are not going to be strong enough at this lower latitude for us to see with that happening. Notice here we have quite a number of areas in Canada, reaching almost down to the upper peninsula of Michigan. If you go there, you'll see them quite frequently. Notice over in this corner here, we have Iceland. Iceland gets them all the time. So what's happening, of course, is we can measure solar storms and tell whether it's likely to be a good night or a bad night for solar storms hitting the Earth and giving us northern lights. So they actually have a scale. And when you're in the hotels in Iceland or the Upper Peninsula, Michigan, or other things that advertise northern lights, they'll give you a numerical rating as to whether or not it's worth going out to see. When we see the solar cycle, this is done in a magnetogram, which is looking at the magnetic forces on the sun. We can sort of see over the course of 11 years, we go from sunspots to no sunspots to sunspots again. One of the things that happens, of course, is the sun is rotating, but as it's rotating, it's not solid. So in fact, the area around the equator is rotating faster than the area at the poles, which means if you start out, say in day 1, year 0 here, you're going to have a North Pole and a South Pole, and everything's going around. But as that continues, the lines are going to get warped and warped and warped until 6 years or so into it, they're no longer going to be vertical, they're going to be horizontal. And when you reach that, that's when you reach all of the sunspots being formed. Well, as that continues on in the other direction, by the time we reach the end of an 11-year cycle, they're going to be straight up and down again. But by that point, the north will be at the bottom and the south will be at the top. The north and south poles of the sun flip every 11 years. Again, it's not solid. It's not solid. So as we're looking at these different kinds of things, again, here we have light being put through a certain filter, a certain prism. We can see this white stuff around here. This is called plagues. And they're not plagues in the way that we have like coronavirus plague, because there's no U in here. But one of the things that we see is that these are from calcium. There's not a lot of calcium on the sun, but there are trace amounts. There's not a lot of anything on the sun except hydrogen and helium, but there are small amounts of carbon and small amounts of calcium and small amounts of iron and small amounts of pretty much all of the other elements that are naturally occurring. When we look at these things that are being thrown off the sun, we sometimes call them prominences. Again, the size of the Earth is here. Notice it loops around. The magnetic fields are holding these in place. Sometimes the magnetic fields get twisted. I like this lower left picture here. That's part of what we can see in terms of the magnetic fields that are happening. Here we have a solar flare that's happening, a big, big explosion that'll sort of throw out extra particles. Great for northern lights, not so great for radio reception. In fact, in the early days of cell phones, they used to give a daily update on solar flares and the likelihood that your calls were going to be disrupted because our technology wasn't as good back then. Here we can see, if you look closely in here, a twisty solar flare explosion. This is going to be 1,000,000 times more powerful than a big eruption here on Earth of a volcano. Here we can sort of see some flares, and look at this in C. This looks like half the sun is falling out of the bottom here. But the truth is, this is more like a soap bubble filled with energy. So not a lot of stuff that's actually there, but it's being spread out, and those extra particles are going to hit our atmosphere and give us quite a bit of a show. Here is the sort of last complete solar cycle that we have. Our latest solar cycle that we're in was actually delayed by a couple of years, and people wondered if we were entering another Maunder minimum, and then they started up. So probably in the next year or so, maybe even later this year, we'll have another complete cycle from like 2008 to 2020 showing this. But notice 1996 down to 2001, giant sort of solar cycle flares and sunspots, down to 2006 where it's calmer again. And right now we're in another calm period. So because by the time you generate 12 to 13 years from one calm period, you're in another calm period. Now here's the danger. We don't really want to be going to the moon when it's like this, because you don't have an atmosphere on the moon, and that atmosphere that we have protects us from a lot of the energy and radiation that's happening here. Now, let's say this is 2020, 2021, 2022, 2023, 2024, 2025. Guess what? NASA says we're going to be going to the moon in 2024 and 2025. That's not really great. But if we wait till 2026, 27, 28, 29, that's going to be an okay time to go. And here's what I think about NASA. No offense to NASA, but when they say they're going to go somewhere in 2024, chances are they're going to get there in 2028 to 2030. So I think actually the real plan, the realistic plan, is going to get there when it's best. One of the reasons why I say that is because, like the James Webb telescope that I've mentioned before that's supposed to replace Hubble, was supposed to be up there more than a decade ago. Some things run late, and I'd rather they run late and then run well. That's especially true of moonshots. But I think one of the things that we need to be realistic about in terms of returning to the moon is that it's going to take a little while longer than we thought. That's actually a good thing. That's actually a good thing based on this. If we look at the solar regions or the solar activity in a particular region in different lights, we can sort of see different magnitudes of our explosion taking place here, depending upon how we're looking at it, the different kinds of power and forces that are coming off of it. And one of the things that happens, of course, is all of this energy creates a shield for us. We have these particles that are streaming out from the sun. They're going every which way, 360 degrees, so we're inside a bubble. And when we launched the Voyager spacecraft and the Pioneer spacecraft, the Voyager spacecraft, well, not, come back here. I want to go back, play from current slide. Nope, okay. It's going to create some problems for me. Okay, I'm going to go back to this. The Voyager spacecraft and the Pioneer spacecraft are both interplanetary spacecraft that explored Jupiter, Saturn, and for Voyager 2, Uranus and Neptune. And after that, they both went beyond Neptune, all four of them actually went beyond Neptune. Voyager 1 and Voyager 2 are still communicating with us. And what they're charged to do now is to figure out where this place is, this heliopause. Because our sun, as it's going through space, is actually going around the center of the galaxy. Takes about 250 million years to do that. As it's doing that, it's hitting interstellar gas and dust. We're mostly protected from that because the energy of the sun as it goes out is creating this bubble. The same kinds of particles that are hitting our magnetic field and creating the northern lights are creating this bubble. Well, as we sent out the probes that are out there, we had Voyager 1 go sort of in this direction. We had Voyager 2 sort of go in this direction. We wanted to get different areas that we might be able to understand as we're going through the galaxy. And we're actually going up and down and up and down and up and down. We're not just going straight across. We're going in a, if you've ever seen a warped record, a warped vinyl record that's been left outside, that's how we're going up and down. But we're bumping into this gas. Here, this whole thing here is called the heliosphere. And this is generated by the sun. Now, our Voyager 1 and Voyager 2 spacecraft have reached points where the energy that they are assessing and the particles that they are reading are more from interstellar gas than they are from the sun. That's only been true for the last couple of years. So it's taken them 40 years to get to an area where we're starting to get more stuff from the outside than the inside. So we're getting a good definition of where this area begins. And what we're finding is we have pockets where it's more the sun, then more outside, then more the sun again here, then more outside, then more the sun here. So it's almost like we've got this sort of bubble wrap where we've got areas that don't have bubbles in it along the way. And that's an unusual find. We didn't expect that to be found. But as we're going through, this blocks a lot of stuff. So we don't see a lot of stuff coming in to the inner solar system from outside, unless it has a weird trajectory and a lot of momentum. So just a couple of years ago, we had something come through, not like this, because that'll be bounced off. It came through on a trajectory like this. And it was called Oumuamua. And Oumuamua is a Hawaiian word. It was discovered, if you remember, way back in chapter 6 when we were talking about telescopes, and I showed you the Keck Observatory in the mountains of the Big Island of Hawaii. This was discovered there. It was discovered, it was sort of going in this direction and this direction. It was sort of discovered here. So it wasn't even discovered on its way in. It was discovered on its way out. So we didn't have much time to analyze it. But when we're looking at different things in our solar system, we have letter designation. So if it's an asteroid, it's an A. If it's a comet, it's a C. If it's a planet, it's a P. Well, what were we going to call Oumuamua? They decided we would have it as an I. It's the very first I object for interstellar. And because it was coming from this direction and going at this direction, it was going too fast to be caught by the sun. If it was going a little bit slower, it might have ended up in orbit of the sun. But because it was going fast, it went through really fast. It shot through what we call the bow shock here, and it bounced through. It got bent. Its trajectory got bent just a little bit, and it probably picked up a little bit of momentum from the sun as that happened. We do that with our spacecraft. And it's still out there, receding away from us. It was sort of cigar-shaped. People are still debating whether it was a comet or an asteroid. But look up Oumuamua, and that would be an interesting final project as well. But that was the very first I. We've since discovered a second I. And we may have discovered a third I that when it came in, got caught by Jupiter and started orbiting as one of its moons. So that's still being debated as well. So there are different things that we are finding, just sort of like finding Oumuamua. We now look back and say, hey, that thing there sort of looks like that too. So we may have actually seen a couple before we even knew what we were seeing. But this keeps us relatively safe from a lot of the stuff outside. Obviously, it's not an impenetrable shield by any means, but it's helpful as well. And every star does this, and every star as it's moving through the galaxy has its heliosphere, helio meaning sun or star. and heliopause is where it bumps up against the interstellar gas. And on that note, I think that's a good time for us to stop, because that is our last slide. And if you want to know anything more, please join us for 102. The 102 class is occasionally offered online. It is offered in the summer of 2020 online. It will also be offered in the spring of 2021 on campus at Bloomington. It isn't offered very often by Ivy Tech, but and Bloomington is one of the few places that offers it. But if you take that class, guess what? This is actually your introductory chapter. This is one of the first lectures. I give a more general thing, but this is the first one. So hey, you'll already be 2 chapters ahead.